Yeah. Okay, thank you. Thanks for organizing these much-needed scientific gatherings in these times of social isolation. And actually, for once, I'm quite happy to be talking toward the end of this conference, because my talk is more focused on what is, in my view, the future of numerical simulation at the epoch of reionization. So this is my attempt, actually our attempt, because it's not my lone effort, but it's together with Rahul Khanna and Aaron Smith mostly, but many other people around the world, to build what we think is the next generation of numerical simulation. So as you see from the title, these were supposed to be called the MoRiA simulation. We spent quite a lot of time thinking about a nice acronym we all liked. And then just a few days ago, we realized there is one single paper in 2017 that uses the same acronym. And so we decided to change. And these are now the tests and simulation from the Etruscan goddess of light. Okay. So what are these simulations? Let me start with a plot that was discussed actually yesterday. This is the cross-correlation between the Lyman alpha transmitted flux along a quasar sight line and the position of galaxies around these sight lines. Romain Meyer did a very nice job in explaining all the details of this. What I want to point out here is that in a previous attempt that I published last year, I tried to reproduce this feature, this enhanced transmitted flux at intermediate scales from the Kroc simulation, and I failed. The simulation here are the white lines, and so as you can see, there is missing flux. Now, this, together with many other scientific drivers, brought me and my collaborator to think a bit what we can do to improve on current simulation. And the problem here is that these simulations are now so expensive that we cannot just afford to explore the parameter space. And so we need to try to be a bit smart. So to explain you what we decided to go for, let me just pull up this picture. You have seen this hundreds of times. I'm not gonna explain it. What I want to point out is that numerical simulation can be categorized in two different classes. One is where the majority of them are simulation focused at low redshift, for example, Illustris, Eagle, and so on. And by focus, I mean that they are calibrated and run and tested at low redshift and often miss the physics to explain the high redshift. On the other hand, the simulation that focus on the high redshift and on the epoch of reionization in particular often have all the physics needed, but they are rarely tested all the way to redshift 0. There are obviously exceptions to this, but I think there is a missing connection many times between these two, between early and late universe. And so this is one of the reasons why we are devising a new simulation set. We are trying to bridge this gap by using a galaxy formation model and dust model that were developed and tested at redshift 0. So they have been thoroughly tested, and then we complemented them with the radiation transport needed to study the epoch of reionization. This model is the Illustris-TNG galaxy formation model. Just briefly, it builds upon the Arepo moving mesh code as mass, energy, and metal return from supernovae in the AGB stars, explicitly tracks 9 metal species, as magnetohydrodynamic, bimodal black hole feedback, and stellar winds. So what is missing to study the epoch of reionization is obviously radiative transfer. This is just an overview, though, of the many properties that the TNG model can reproduce at low redshift. So we can build upon a model that is able to reproduce a large variety of observed properties where the observation have exquisite quality. But we need an extra piece of physics, and this is, as I was saying, the radiative transfer. So Rahul Khanna actually implemented a moment-based M1 closure method in Arepo. We have photons from both stars and QSOs and multi-species non-equilibrium chemistry. And the bottom right, you can see that this method is not only precise, but also actually quite fast. So we only not only quite fast, but also precise. With only 32 squared cells or resolution element, we can reproduce what Ramses-RT yields with 1024 squared cells. And the other piece of physics that we included is dust. So the dust model from Ryan McKinnon, again, was tested thoroughly at redshift 0 and performs well. You see the dust mass function compared to observation on the bottom right. And so we just take this model and implement it in the simulation. We don't touch any of the parameters. So in this model, we have dust creation from stellar yields and grain growth, and dust destruction from supernovae and thermal sputtering. But we also want to bridge the gap between large boxes needed for the statistic and the high resolution needed to study the details of the galaxy. And so we use this simulation strategy. We focus most of the computational time on a large box simulation of 100 megaparsec on a side, 10 to the 6 solar masses in dark matter resolution, complemented with smaller runs where we explore physics, say the escape fraction models, early versus late ionization, and so on. And then we pick objects of interest where we zoom in, including extra physics at the smallest scale, for example, going beyond the equation of state approximation that was discussed yesterday, or studying the Lyman alpha radiative transfer, like Aaron Smith showed yesterday in his talk. And finally, we want also to bridge the gap between simulators and the community, and so we plan to make all the data available once these simulations are finished. One last bit of technical detail, we use fixed initial condition, which means that unlike normal initial conditions, we don't sample the power from a Gaussian distributor centered on the expected value, but we exactly fix the power at each and every k to the expectation value. This basically means we are sampling the average universe, that not only has the average density of the universe, but also the average power spectrum. This has been shown to suppress a lot the variance, but not affect any of the statistical properties. Okay, so this is the mandatory movie from the simulation. You see dark matter, gas, and stellar densities on top, H1 fraction, temperature, and photon density on the bottom. So you can see the reassuring picture of ionized bubble that emerge from the first objects and then percolate and create and reionize the entire universe. So let me just focus on two of these panels. One is the ionized hydrogen one. So from here we can get the ionization history of the universe, and this is the only this is the quantity that we use to fix the only free parameter in this model, which is escape fraction. And once we fix this escape fraction, everything else comes out naturally from the model. So I'm showing here the UV luminosity function for galaxies at 3 different redshifts, 6, 7, and 8. And you can see that our simulation, which are the solid lines and the shaded region, actually reproduce quite well the observation, which are the symbols. So in this case, for simplicity, we have just included an empirical dust correction, but as I mentioned, we can do better because we have dust. And to show you what dust does in the simulation, I've plotted here the dust mass versus stellar mass. The blue points are from the simulations. The lines are the median and 1 sigma around it. And the symbols are, again, measurements from observations. And so you see that in the high mass end, where our simulation overlap with available constraints, we are actually doing quite well. On the right-hand side, we have the prediction for the dust to metal ratio as a function of metallicity compared to some of the models available. So we seem, for example, to match quite well with the Vijayan 19 model. But what I want to show is that we do not only have the statistics to look at these galaxies, but we can zoom in. And actually, I forgot to say at the beginning, all the results I'm showing are based on a simulation or a calibration run, which is a factor of 8 away in resolution from the target one. So you can see that we can pick the largest object in the simulation, for example, and zoom on it and still see a lot of details. We have the gas density, gas temperature, dust to gas ratio, and neutral fraction in these panels. So you see the quantity of details that our huge numerical effort actually brings up. Okay, so this is a laundry list of what we want to do with the simulation. We go from the Lyman alpha spikes to galaxy correlation, which was, as I said, one of the drivers of this simulation set, to 21 centimeter galaxies correlation, high redshift dust and magnetic fields, because I just mentioned that in passant, but we have magnetic fields in this simulation. As Aaron showed yesterday, Lyman alpha radiative transfer, high redshift metal lines, because we have metal tracking, so we really know how, like, the relative abundances of metals. And then let me just mention that when you combine MHD and radiative transfer, you actually can explore new magnetic field seeding mechanism. I don't have the time to go into the detail, obviously, but if you have any idea, please talk to us. This is an ongoing effort, so we are very open to any suggestion and idea. Before concluding, let me just spend 1 minute on a different effort I've been working on, or a different thing I've been working on. This is called CoreCon. just came into being from the randomness of my collection of constraints. I had them scattered around different computers, different folders. And at some point, I decided to homogenize them in the units and in the format. And so this became a Python package that is now available. You can install it. You can look at the documentation online. And most importantly, I decided to make it as easy as possible for people to add their own constraints. So if you have any constraint related to the reionization, you can just go or look at the documentation and put in your constraint. With that, I just leave here the summary and take your questions. Thank you.
Thank you, Enrico. So Sultan Hassan asks, do you run RT on a grid or particles, like C2 or like traffic, and how fast is it?
Okay, so we run on the RT on the Voronoi tessellation that is used by Arepo. So it's a grid, but it's not a Cartesian grid; it's a Voronoi tessellation. This is moment-based, so you basically treat you solve the moments of the radiative transfer equation. Regarding the speed, well, it's radiative transfer, so it's slow, relatively slow. So just to give you an idea, is roughly a factor of 4 slower than the hydro part, which is actually quite great. I would say, but also this depends a lot on the resolution and on a lot of technical details. So depending on the, for example, on the simulation box, it will change a bit.
Okay, Chris Lovell says, looks amazing. Do you run the same initial conditions to z equals 0 with less physics to see what the descendants are?
So as I said, this is still an ongoing effort. We definitely will do that. We haven't yet. We have run, you know, sorry,
go ahead.
I just want to mention, I forgot, we have made comparison to down to redshift 5.5, running with and without RT, so the original model and ours. We haven't still run till redshift 0, but we'll definitely do that.
Okay, Aswin Bijayan asks or says, really nice talk. What changes do you get from TNG on adding RT and active dust? Also, what attenuation curves do you get from the dust distribution in the simulations?
Okay, so regarding the differences, we don't get actually much difference. So very small differences in the smallest galaxies, but I should say that we are still a factor of 8 away from the target resolution. And the target resolution is the minimum resolution to resolve these atomic cooling halos. So we don't expect, we expect to get more difference, more differences when we reach the target resolution for our simulation. So I will hopefully answer that question in a few months. So the other one was the attenuation curve. I don't know yet. As I said, so this is more about the future in the sense that this is the plan. We have run some tests, but yes, we haven't actually carefully looked into that yet. But thanks for the suggestion. I will definitely do it.